Okay, so this is hello everyone. So this is going to be workshop number 3 in your molecules of medicinal importance set. So you had workshop number 2 last week, parts 1 and 2, so hopefully you found those okay. Again, you might not have even got to them yet, so hopefully let me know how you get on with that particular side. Remember, both me and Professor Osborne are contactable if you have any particular problems. So again, if you want to go through any particular questions or if anything's still not clear, please just let one of us know. So this is the third one. Now my plan is to skip in or redo at least workshop number 1 as well, just for completeness, just for my own peace of mind. I know you've gone through that one in class, but again, just so the full set is there, I think I'll probably end up recording that one as well, which might be helpful to some of you. So this third one's all about heterocyclic chemistry. And again, it's about introducing these sorts of concepts and these types of molecules, seeing why they're important in drug discovery or drug development, and making you more confident with how to handle them, how they react, and all those sorts of things, because they're super important in terms of how drugs are synthesized or how they react with particular targets and all those sorts of things. So it's important that we have covered these kind of key factors. In terms of the learning objectives, we'll start the fairly straightforward kind of points, which is looking at what aromaticity is. So again, getting used to dealing with some of those terms, again, you might not have thought about for a little while, but again, it gets you used to those sort of simple definitions of chemical terms. We want to describe reactions with both pyrrole and pyridine. So we'll have a look at those two molecules in particular. Again, the lecture's focused on those particular two because they are important and they're used in lots of drug molecules. And then finally, we'll look at how to synthesize those particular heterocyclic compounds. We're probably going to focus on pyridine, but just to show you how actually we come up with these in the first place. It doesn't necessarily mean that they have to be naturally occurring structures for us to be able to use them. We can synthesize those from earlier points as well. So there's a few different bits for us to focus on there. So the first part we're going to look at is a bit of a revision on aromaticity. So we have a look through the questions. The question is, what is a heterocycle? Okay, so not initially dealing with aromaticity, but we're looking at heterocyclic chemistry. So what is a heterocycle? And then I want you to illustrate your answer by drawing an example of an aromatic heterocyclic compound. Okay, so the question's got a few different points, I suppose. So we want to look at what a heterocycle is. So a little bit of a definition there. And then we want to see whether you know what an aromatic compound is, and also whether you can link that into a heterocyclic compound as well. So can you add these sort of different concepts together and come up with a suitable aromatic heterocycle? Okay, so we'll look at what a heterocycle is first. Now the terms, or the way the word is written, you can basically split it into two. Hetero in chemistry always means difference, so it means that something's different in the molecule, and cyclic or cycle means that it's a cyclic molecule. You're used to probably cyclic molecules, okay, so these aren't new things to you. You'd have seen things like, I don't know, cyclohexane, cyclopentane, and you remember that when you see these, they're cyclic in nature, okay? Apologies for my slightly terrible drawing of cyclic compounds, slightly tricky here, but that would be a cyclic compound, okay? These are all carbons here. It's a little bit hard to show you when I'm drawing them by hand, but it's a cyclic compound, okay? It goes round in a cycle to join up again. So this would be cyclopentane there. We've got 5 carbons involved. Now what we're actually looking for is what is a heterocycle. Now if you want to look at what the definition is, okay, so the definition of a heterocycle is a compound that is cyclic, which contains one or more non-carbon atoms. Okay, so if we looked at it, or we tried to apply that definition to this cyclopentane, yes, it is cyclic, so it ticks one of the boxes. But does it contain a non-carbon atom in the cycle? And that would be obviously a no at this point, because they're all carbons. So important point is this cycle, or this heterocycle, must contain a non-carbon atom in its ring structure. So the easiest way to change this, and this is just an example of a heterocycle to start with, I know that's not necessarily what the question is asking for, but if we put a nitrogen at the peak of our ring, okay, now that turns it from being still cyclic in nature, But now we've got a heteroatom, so this would be our heteroatom. It is different from carbon, and therefore we could class this as being a heterocycle. Okay, so this one at the moment is just a heterocycle. I'll write that out full. Okay. So if we move on to the other questions, asking you to illustrate and answer by drawing an example of an aromatic heterocycle. Now this compound right here is not aromatic, and we'll get to the reason about why it's not aromatic shortly. But just to say that there's a combination here. The most common aromatic compound that you're probably used to, if I can just draw it out here, is probably benzene. Okay, so it's a 6-carbon structure, and we denote it's aromatic with these double bonds here. Now these double bonds aren't actually real. What it's saying is that those electrons in the cyclic bonds are kind of all linked together here. So the electrons are being held in kind of this middle cavity here. It's what we call a conjugation. So these are fully conjugated in terms of spreading the electronic force throughout the ring structure. So this would be aromatic. But if we go back to our heterocyclic definition, this is not heterocyclic because all the atoms in the ring structure are carbon. Alright. Now you might just say, I'm going to get rid of a few of our structures here. Can't we just replace one of our carbons, they've all disappeared now, with heterocycle or with a heterocyclic atom? So the heterocyclic atoms we're used to are oxygen and nitrogen. That's what we're going to talk about particularly in these ones. Which is right, but there are certain rules that have to be maintained to make sure that it still obeys its point of being aromatic. So there are 3 key rules that you need to apply, and we'll put them in practice in a minute. Okay. So those 3 key rules is that it has to have 4n plus 2 pi electrons. Okay. And then we'll come through to that in practice in a second. Secondly, the electrons are fully conjugated. Okay, and again we'll look at what that is. And number 3, it's planar in sort of configuration. Okay, so they're the 3 rules that you need to apply to say whether something is aromatic or not. If we go back to benzene, because it's the easiest one to start with. Okay, I'll draw in the double bonds here. So 4n plus 2 pi electrons. And you might think, well, what is this for? What is this n? In reality, n can be any number. Pi electrons are obviously the pi electrons within the double bond, or remember those sort of electrons that are being held in the centre here, the pi delocalization. Now n we can just give any number in reality. So if you make n equal to 1, what does this equation equal? Well, you get 4 times 1 plus 2. Okay, so that is equal to 6. If n was equal to 2, you get 4 times 2 plus 2, which is equal to 10. And again, you can go 3, 4, 5, 6. So actually it's just going up in nature. The n doesn't actually reflect anything in particular you need to measure. It's just saying that it must be one of those, it must be an integer to allow you to know how many electrons are involved. So if we have a look at how many electrons are involved, or how many pi electrons we have, this is why we often do it in double bonds, because it's easier to count or at least record. So each double bond would give us 2 pi electrons. So if we count them up between them, that will equal 6 pi electrons. Perfect. So in benzene we've got 6 pi electrons. Now for 4n plus 2 pi to be true, it has to be one of these numbers. Again, it could be 3, so it can continue. 6 here matches a 6 here. so it obeys that rule. Electrons are fully conjugated. Okay, the electrons of the bond are fully conjugated. Again, if we drew it in that sort of conjugated style, all the electrons in the bond are being held within the structure, energy is being spread out throughout that ring. Okay. And number 3 is that it's planar. Now that can be sometimes a little bit tricky to see, but what I mean planar is that it's not like in a boat formation that we have like here where bits are sticking up. This is flat in nature. Okay, so we don't have any differences in sort of angular dimensions like you might have with other molecules when we draw them in this kind of way here. So it's flat in nature. Sometimes that's hard for you to see, but if you have this kind of strict ring structure, everything is held in that flat plane. Alright. So that deals with what an aromatic structure is. Aromatic, it just has to obey these 3 rules. If it doesn't obey one of them, then it's not aromatic. So all 3 have to be correct. Obviously, we're saying it needs to be an aromatic heterocycle, so it also has to have the heterocyclic element in it here. So the ones you could have drawn, there are lots of different options here, so you could have come up with many different things. Most common ones, if I draw what would be almost a benzene, I suppose, but we replace one of the carbons with a nitrogen, just like that. We'll put you there, and you down there. So that structure there is pyridine, as we'll look over that in a bit later. So that's a common one you'd have come up with. You could also come up with Purine, which has our nitrogen here. Now where things will get confusing is that you might not think, actually, when you count up how many pi electrons we have, and we'll use it in our next example, you might think that actually this only has 4. That doesn't obey our equation here, because the lowest number that this could equal is 1, which gives us mean the lowest it has is 6. But remember, we also need to think about lone pairs. Nitrogen has a lone pair that it can actually donate into the conjugation or delocalization. So they are actually included if I drew a little circle around where the atomic energy is. That's how it's spread out in Purine. Now, I did say that we'd generally focus on oxygen and nitrogen, but you can use sulfur as well. So this is thiophene if we draw in those. You can have an oxygen derivative of that as well. So this is furan. And again, it can become even more complicated as you want in reality. So we could draw indole, and again, all these examples are given in the answers that you will receive as well. The nitrogen is just down there. Okay. So it's not always just spread across one ring structure that you need to think about. Okay. So these are all examples that would be relevant. Now I just want you to draw them. I don't need you to name them, so you don't need to learn the names especially, but it's useful that you remember this is pyridine here, we've got pyrrole here, furan will come up, not so much thiophene, but it's important that you know other structures included. So if you do know some of the names, it is important. This is indole up here. So again, you might just see these in drug structures, and therefore you might just want to know what they are. Okay? So we'll move on to section 2 now, or question number 2 even. So we've got some examples here, or actually the second part of the first question I suppose. So we've got some examples here, and we want to work through those criteria. So you can remember the 3 criteria we have here, the 4n plus 2 electrons, the conjugated electrons, and there's a planar structure. And you want to state, or I'd like you to think about, whether these would be defined as aromatic compounds or not. Okay? So remember, importantly, do not forget about lone pairs that still could be included in the the sort of pi electron structure, okay? So make sure you're not forgetting about those. And again, I'll try and point some of those out when we have there. So it's always useful to store in lone pairs sometimes with cyclic structures to see whether you think they are or not. Okay. So we'll start with number one. So number one is actually purine, okay, the first one. So this one's purine here. Again, the name's not particularly important, but again, we'll start over here with purine. So if you remember, number one was our 4n plus 2 pi electrons. So we'll count what electrons we have. So for sure we have 2, 4, 6 and 8. Now if we go up to the top, you can remember if n is equal to 1, that means there's 6 electrons, and if n is equal to 2, it would give us 10 electrons. So we know that in reality our structure needs to have 6 or 10 pi electrons. Now just from counting the double bonds, or denoted by the double bonds, we have 8. Now the other thing we need to remember is that nitrogen has a lone pair, and the way that everything's spread out, this lone pair is actually included in the pi delocalization. Okay, so if I was going to draw a ring around, what happens is it sort of links these parts of the structure up around here and uses those lone pairs to delocalize. Okay, so if we're counting them out, we need to also count the electrons in the lone pair, which would give us our other 2. So our 4n plus 2 pi electrons for this structure is equal to 10, which is true. We know that 10 is a valid number for that. Perfect. So we go to what our second rule was. The electrons are fully conjugated, which they are. We've got the lone pair of the electrons are being included, and everything else is also fully conjugated. So it's a tick for number 2. And number 3, it's a planar structure. So as you can see, there's no arrows here denoting that it's in any sort of form other than flat in nature. So it's also a flat ring. Okay, so we get a tick for that one. So from that, we'd say that this is definitely an aromatic structure. And I know that purine is aromatic. Okay. So we'll do this now for our next structure. So moving on to this one here. So let's have a look at what electrons we have involved and those kind of things. So the 4n plus 2 pi electrons, well, we know for sure we've got 2 with the double bond. Now, you'll know that oxygen has 2 lone pairs. Now, remember that they need to be spaced out evenly. So remember, they all try and separate out as much as possible. So the lone pairs in oxygen are going to sit here and here. Okay? So they're not actually involved in the ring structure at all. They're outside the ring. These would be free to bond with other particular atoms. Remember, the lone pair in nitrogen that is delocalized here is not free to bind or to bond with another atom. These 2 would potentially. So we actually only have 2 pi electrons. Obviously, we know that it needs to be 6 or 10 at this stage. So actually, it doesn't abide by that rule. Okay, let me just get rid of these 2 ticks here. Next rule, are the electrons fully conjugated? No. So we've got electrons in these bonds, they're not being spread out. There's no kind of ring delocalization we have. These lone pairs are not included. So no, all the electrons in that ring structure are not delocalized or conjugated. Is it planar? Now, from the way we've drawn it, you wouldn't be able to see. You'd say, well, maybe it is. But actually, if we were to draw this out in reality, we'd have bits pointing up and pointing down in the structure. So it'd actually look almost like kind of like that, I think, in nature. Almost like our chair or our boat formations. So also, it is not planar. So it doesn't abide by any of the rules. Now it is cyclic, okay? So we'd still call this a heterocycle because it's got a heterocyclic atom and it is cyclic in nature, okay? So we call it heterocycle but it's a non-aromatic heterocycle. Okay, so this is actually a pyranol molecule. So the pyran part is our ring structure. We've got an oxygen, hydroxyl, so we've got our ol is on there. So you might see these occasionally in drug structures. Okay, let's move around onto our next one. 6 or 10. Now remember we've got the lone pair. Remember how they're going to separate out. The hydrogen's outside, sort of here-ish. So our lone pair is going to be held in here. They would all link up in our conjugation. So how many electrons do we have? Well, actually, we've got 2, 4, and the 2 lone pair, which gives us our 6. So there's a tick for that. Are all the electrons fully conjugated? Yes, they are. They'd form this sort of inner conjugation ring, or pi system. So there's a tick for that one. And is it planar as well? Well, again, you can think about the double bonds always hold things fixed in place, and actually that's why we often draw them like this, is that it's showing that called fixed position, and it would be held in a sort of flat particular plane. So it is also a tick for that. We'll move on to our last one. Again, you probably recognise that one as being Purine. So we'll move on to our last one, okay, which is our imidazole ring. Okay. So again, our offset, you can see there are 2 particular ones here. Okay. We've still got our hydrogen off our nitrogen at the top, so we've got a lone pair here, and we've got to have a lone pair. You might think we have a lone pair involved down here potentially. Now remember how they're going to spread out. The lone pair of this nitrogen is going to be sitting outside. The lone pair on this nitrogen is going to be sitting inside. Remember, it has no, well, it'd have a bond available, or potentially you might think, oh, it has some sort of affinity or lone pair that could bond outside of here potentially. Okay. Now remember, it's actually bound potentially to 3, but these electrons here are going to be sort of held in with this double bond that we have over there. So we can actually kind of ignore any sort of lone pairs around that structure, because those lone pair you might push out here if you're trying to separate them if that double bond wasn't there, but in reality they're being held in this double system that we have over here. So again, if you were trying to link everything up, they would join up via the lone pair, and we have pretty much the same as we have in Purine here, where we have our 6 conjugated electrons, or pi electrons. It's fully conjugated, so all the electrons in that ring system are spreading out the charge, and it is flat as well, so there's no way that this could be pulled up or flipped down. Okay, it's going to be flat in nature. So this one would both be aromatic, and so with this one would not, this would stick, it's just a heterocyclic compound. So it's quite easy when you get some practice in terms of doing that and trying to spot what it is. Again, you'll see lots of these molecules come up again, and so you won't actually always need to work it out. You'll just know that if I see a Purine molecule, I know that it's aromatic. So there's a little bit of knowledge in there as well. Okay. So we're going to move away from sort of our definitions, I suppose. We're going to move into describing some reactions with pyrrole and pyridine. So this is pyridine down here, which you remember earlier, it's the sort of 6 ring structure with our nitrogen heteroatom right here. So pyridine and pyrrole, so both shown below, but we've got this one up here as pyrrole on the next slide. Okay, shown on the next question, fine. They have quite different reactivity profiles. So the reaction we have below is a reaction of pyridine, okay, here, with methyl bromide. Okay, so I haven't drawn the CH3 here because we don't have to. Remember, we don't have to draw in all the implicit hydrogens and everything like that, but they are there. Okay, just how we denote the CH3 group. And what the question is asking is to draw a curly arrow to show how the products from the reaction form. So this is what happens when we mix those two together. And we want to know is how we get from our starting materials to here. And again, we need to identify what the nucleophile is in that particular question. Okay. So we need to think a little bit about lone pairs, how they're kind of involved, and all those sort of key factors that you have here. So pyridine actually has a lone pair that sits outside of here. So nitrogen has our lone pair sitting out here. It's not needed for this pi electron system here, so it can be held out on its own almost. So it's important that when you have this, as you draw those lone pairs in. Now we know bromine being a very electronegative atom, so if you think about how the bond's going to be polarized, the electrons are going to be formed towards, so you basically have a delta positive and a delta negative here in reality. So electrons are going to be much closely associated with our bromine than they are in our methyl group. Okay? So we did some practice in terms of showing how electrons move in our last workshop. But just to say, obviously the arrow always shows the movement of the electrons. Now this lone pair is actually free to bond, potentially. We've got some electronegativity here, and this is wanting to strip the electrons from the bond. So what we actually get is the lone pair be able to go to our delta positive on our carbon. The electrons from the bond then go to our bromine. So now we have a bond being formed between the nitrogen group of pyridine and our methyl group, and then we have our Br minus now being formed as it forms here. Now remember here we're showing that nitrogen is now forming 4 bonds. Obviously you're getting a positive charge on our nitrogen molecule, which is why we give them those charges. So we want to say what is the nucleophile in this particular reaction. And potentially we're looking for a nucleophile, anything that's drawn to something that isn't electron rich in reality. So potentially you could say that this is acting as a nucleophile because it's drawn to our carbon, which is not electron rich. So that's the easiest way to denote the nucleophile potentially in this reaction. It's the opposite of a nucleophile, an electrophile. Which would obviously look for electrons in our structure there. Okay. So we want to look at why this reaction occurs, and the key factor here is that we have our lone pair on our nitrogen. If this lone pair was included or needed in the ring structure that we have, so if it was included in here, obviously this isn't real because that would never happen, but if it was, they wouldn't be free to bond with our methyl group. Okay, so it's important that we remember that. So it's that free lone pair of electrons, or the lone pair on the nitrogen, that allows it to act as our nucleophile and mix to our methyl group on our methyl bromide system. So I hope that's fairly clear. Make sure your arrow is always denoting where electrons are moving. So we're going to move on to pyrrole now. So pyrrole reacts readily with electrophiles. Okay, so a little bit different here. And if you think about pyrrole, so we just go down to where pyrrole is, we need to remember that the lone pair is included in the system now. So it's not free to do sort of any other bonding with anything else, with any other atoms. Okay, they're locked in that ring structure. So the question is to complete the reaction scheme below for the reactions of bromine, or bromide, sorry. So Br2 are both the 2 and 3 positions. And at this stage it wants you to also identify what the electrophile would be in this case. So the first thing you need to do is you need to know where positions 2 and 3 are before you can really even answer the question. The numbering of these sort of cyclical structures always starts from the heteroatom. So we've got this number 1, this becomes number 2, and this number 3. In reality, it doesn't matter which way round you go, because you could also call this number 2 and this number 3. Alright, so you don't need to go round in a ring potentially, because again, if you flip the molecule over, it would make no difference. Okay, so don't worry too much about exactly how you're numbering them, but this is going to be 2 and 3, and this is going to be the same on this molecule down here. Okay, so we're saying that it could potentially react at either of those two positions to make two potentially different molecules. So if we draw it, if it had reacted at position 2, and what you think would form, we'll get something like that. The pyrrole, don't need to draw the lone pair in. So if the bromide acted at position 2, we'd have a Br or bromine here. Okay. And if it reacts at position 3, sorry, should put my nitrogen there, you'd have a bromine in this position. Okay. So we're not going to worry too much about necessarily how or why they would necessarily favour one or the other. They will come to that in a minute. But at the moment for this question, we would say that actually there's still going to be potentially a split in the bromide molecule. Randomly, one will become delta minus and one will become delta positive, just as electrons sort of constantly move around in the system. The electrons will be donated from this double bond. Okay. They're going to be drawn to potentially one of our bromines. So you're going to get a breaking of the bromine molecule, and you're going to get this sort of system that happens. You could also do it for position 3. It actually doesn't look any different, because it's still going from the bond, like there. But obviously where it fits could be either in those two potential positions. Now the important part of the question that we tried to come to is which one of these two is favoured. So you might want to think to yourself why one particular position would be favoured in the other. We're saying that the electrons are coming from the same bond, but do we think that it comes from or prefer position 2 or position 3? Now some people might think, well, maybe position 3 is better because there's more space here, there's less hindrance. Okay, we talk about steric hindrance sometimes, and that sometimes is true. But in reality, it's actually position 2 that is favoured. Okay, attack at position 2. So this is the structure that is favoured in those reaction conditions. And the reason why is that it has more potential aromatic structures that can form. So we can talk about things called resonant structures. So if you think about benzene, for instance, we always draw benzene like this. But in reality, what's constantly happening is that those electrons in that bond are constantly flipping around, these are flipping up, and these are flipping down, constantly looping around, which gives us that sort of spread of electron density. The more that it's spread, the more stable your molecule is, and therefore it is more likely to occur. Okay, molecules always want stability. So if I was going to draw out the different resonance structures that we have for the two molecules, I'm actually going to start with structure number, or the second structure, because it's easier, because it's slightly smaller. So we've already got, we'll just get rid of this as well for the moment, and then we can draw all our steps in. So we'll start with our pyrrole. Okay, it's best that I can draw pyrrole. And I kind of get rid of the bromine parts at this point. is I'll just say that we've got an electrophile of some sort. Okay, it doesn't in reality matter. It would be bromine, chlorine, any of these things can act as an electrophile. So we almost showed the start of the synthesis again, or how we get to our endpoint, or the resonant structures, and we'll show that it's going to bond with an electrophile which has got obviously a positive charge at this point, so it'll be the positive end. The bromine is going to take the negative charge that we're looking up here. Okay. So let's just go through each of the steps, what that physically forms at each point. So if we move it on to our next sort of structure, what do we have at this point? So now we have our electrophile bound. Okay. Now remember, for all of these structures, they've also got one hydrogen bound as well. Okay. So we've still got our hydrogen bound. Yeah. We've lost our double bond here. Still got our lone pair, and this is still bonded to our hydrogen. Okay. Importantly, at this point, is that we've got a positive charge on this carbon here, because again, we've donated those electrons to this section of the molecule, so they've been taken away from the double bond which originally it had, so it's lost its electronic structure. Now what the molecule will try to do is it will try to, through resonant structures, equalize the charge. And what will happen is those lone pair will shift round, kind of like in benzene that it does, will shift round to try and equalize that, or stabilize molecule we have. Now these all shift round. Okay, so I was to draw the next resonant structure. It would look something like this. So the lone pair has now given us our double bond back. We've still got our double bond over here. Our nitrogen is now positively charged. We've got our hydrogen, and we've got our electrophile over there. And obviously this is going to start flipping back almost, so those electrons from the double bond will want to try and equalize or spread out the charge. And what actually happens to make our end product is the electrons from our bond up here get drawn back in, and that's what gives us our final product that we have over here. Okay, that's all stabilized now, and again, so we've gone through those different resonance structures that we have to get from point A to point B. So these two in the middle are actually our resonance structures, so this one here and this one here. So it's got two resonance structures to try and stabilize the charge within the molecule when this end product is forming. If we compare that to what we have in our first one, again it might get a bit cramped, so I have to draw these a little bit smaller to attack at our other position now. Okay, we've still got our hydrogen off here. Okay, the reaction is still almost happening the same, but remember our attack is now at position number 3 rather than position 2. So we still have a bond with our electrophile, but this time obviously we're getting it at its different position. Okay, so now getting it at this lower position, position number 2. So we draw our E and our H here. Okay, remember where we've lost the electrons now. We've now got a positive charge on our top carbon rather than our second one that we had below. Okay, so let's have a look how the molecule would try and stabilise itself? Well, first thing is this double bond, or the electrons in this sort of pi part of the system, will go up to meet our positive charge here. So that's the first thing that will happen. So we can draw what's happening there. So the double bond, what we denote as the double bond, now shifts up. We've still got our H and our E here. Don't forget our lone pair in our hydrogen. And now positive charge is shifted round one, or back one, onto this carbon. Now it's close to our lone pair, so kind of as before, the lone pair is going to try and stabilise by donating in that way. So what does that look like now? It's just about have room on the page to get the last bits in. So we've got a double bond here, and we've got a double bond at the top. Now we've got positive charge on our nitrogen. We've got our H and our E still over here. Now, kind of a similar way that we had before, those electrons will go back to the nitrogen. But now all of these can shift around. They'll go back round to sort of cover up the positive charge. And at this point, our proton will give, or our hydrogen bond, our bond to our hydrogen, will get pulled back into our structure, which again gives us our final product that we have at the very end, with our electrophilic, or half the electrophilic group that we have here. So if we looked at how many resonance structures we have, remember down below we had 2, whereas now we have 1, 2, 3. So we have 3 resonance structures if the attack's at position 2, and only 2, sorry, we have 3 resonance structures when the attack is at position 2, okay, so it's position 2, and we only have 2 when it's attacked at position 3, just to make things confusing. So this would be favoured because it has that extra stability via those resonance structures, and so is more likely to be favoured, or more likely to form. So you may just know, or the question asks you, which 2 products you draw would be favoured. You might just know that position 2 would be favoured. But it's important you start to think about drawing these resonance structures, and this is what's actually happening, or we try to show is happening within the molecule to stabilise the charge. Okay, it doesn't particularly want a positive charge or like positive charges on particular parts of the molecule. It's always going to look to bring them into the structure and delocalise that charge, which is when we talk about resonant structures. If you're not confident with this, go back to resonance in benzene. It's a little bit more straightforward, and then you can move up onto our resonance structures in pyrrole. Okay. So the final question that we have, I'm not going to go over huge amounts of detail in here, but we still think it's important that you know where both pyrrole and pyridine can be gained from, or how we actually form them in the first place, and how the different versions of those form. So this is just a very basic pyrrole, but we can have lots of other substituents on the edges or sides of that pyrrole structure. So this is actually, if we go back up to here, pyrrole and pyridine can be synthesized using the Pal-Nor-Hantz synthesis. Okay, or Pal-Nor for one, or Hantz synthesis for the other. We're showing the Hantz synthesis below. So if you're interested in the other one, you can have a look at it. This is the synthesis that we've shown. So drawing the structure of the intermediates and the final products for this reaction. Okay, so we've got 2 different boxes here to show how you think that pyridine is going to be formed. So I'm actually going to start with the final product almost. You know that you're going to form a pyridine. Alright, so I'm actually just going to draw a pyridine at the end point. Now we don't know how it's, what other bits are attached at this stage, but we can kind of draw the ring structure in at the end. Again, apologies for the quality of the drawing. That's what we have to go with today. So let's have a look at our ingredients, or our starting materials, I suppose I should really call them. We've got this structure here, which is repeated, so it requires 2 lots of that. We've got a carboxylic acid up here, and also an amine down here. Importantly, we've given some reaction conditions. Okay, so this is actually our so it's just to say that these are going to be important in our reaction. Don't actually play any role in what we're going to be drawing, but it's important to know that we'll always give reaction conditions along with our mechanisms. My pen's decided to go walkabouts. Let's see if it will still let me draw. I think it is. Okay. So the first part is to think about what intermediate is likely to form. Now we know that in the structure we have to have had, or we know that for pyridine to form is going to be including this nitrogen here. Okay, so that's going to be an important part of the structure. Now if you look at a couple of the bits in the other starting materials, we have kind of what looks like half a ring here, which is repeated as half a ring over here. So you might start to think that actually these are going to be important in forming our ring structure around our amino group or amine group. Now you can almost think that this is going to give us a top to our ring structure, so that might also be able to close our ring. But the important thing about being able to point out those is it shows just what else is kind of bound to, or what else could be bound to our ring structure. So we've got kind of this substituent here, which might be included. We've got this substituent here, and we've got this here. All the kind of oxygens, carboxylic acid kind of bits, and this, they can all be changed or included in the reaction. So don't always think that they'll always stay exactly the same. But these kind of chained substituents, likelihood is they are going to remain in our sort of final structure. So intermediate here, and again you can look up these syntheses and it will take you through them. Let's just think about what we're going to get formed a little bit. So again, I'm going to start with our sort of starting point of our pyridine. So these 2 points, or these 2 parts, are actually going to form our ring. So they're forming half the ring, and our carboxylic acid is forming the top. So actually on the edges we're going to have this bit remaining. Okay. This part here has been included to form the ring. So you can think about what we've got, sort of this round section here is being formed. The same will happen on the other side. If I can draw it in one piece, which hopefully I can. Oops, I should have put an oxygen there. Okay, like that. And importantly, we can't forget that actually we've got a substituent being added at the top as well. So it's attaching at this carboxylic acid end is what's closing our ring. And actually that is what we're going to be left with at the top. Now you may not know too much in terms of how it's going to look exactly, but I can tell you for the moment we have our double bonds where this is forming, so you can see that we've lost this potential structure here. We have a couple of methyl groups which are pointing out here, which you can kind of see. It will almost be this section here. This bit's almost flipping round to give us that sort of ring system. Just say this is NH at this point. So we've not lost everything in our ring structure. If we move down to what our final element is going to be and how it changes. But obviously for it to be based on pyridine, this has got to go, and this part of the structure has to become aromatic. Okay, so actually it doesn't look too different from what we have at the top. So actually our final combo something like that. Maintain our, oops, let's leave that as a methyl group. They stay as methyl. This is now aromatic. Okay, this is what we would recognise as being pyridine. And we've got all our substituents that are formed on the side based around that ring structured molecule that we have. Okay? So that's important. Now, in an exam question, I'm not going to ask you to recreate these sorts of points. This is more just for your own knowledge, but just to say that actually if you were trying to build these pyridine structures, they are built in this way from these smaller blocks that are combined together to form our ringed aromatic structure that we have in pyridine. So don't worry too much. You can have a look at these two different systems and it will break down exactly how all the bonding happens and how everything is being matched. But it's important just to have at least know that, okay, we're going to need an amine involved. We're going to need these keto structures involved because that's what's forming our ring branch around each other. So they're important. And then we have our topper here, carboxylic acid, which is going to close our ring. And if you go through all the steps, which are a little bit complicated, it will take you through each of those. But at least allows you to predict from some of these starting materials what your pyridine or pyrrole, if we changed these around slightly, would form as our final product. Alright, so that is it for this workshop. Again, the answers will go up, so it will take you through all these points. If you're struggling at all, give us a shout if you're having particular problems. Again, I'd probably say focus on, make sure you're happy with these parts of the questions looking at heterocyclic and aromatics and how they can be defined and how we dispel they're different. And then these two main reactions with pyrrole and pyridine. Make sure you're happy with these resonant structures and why they'll form in our structure. Okay, so that is everything for this session. Again, I'll try and get video number 1 to you at some point, but any problems, let us know, and that is bye for me. Okay, so until the next time, catch you later.